Right now, at this very moment, you are traveling through space at 67,000 miles per hour. You cannot feel it. You cannot see it happening. But it's real. Your entire body, every atom that makes up who you are, is hurtling through the cosmos at a speed that would take you from New York to Los Angeles in less than 3 minutes. And you've been doing this your entire life without ever noticing. That's the speed Earth orbits the Sun. But that's just the beginning. The Sun itself is moving through the galaxy at 490,000 miles per hour, carrying you along with it. The galaxy is moving through space at speeds we're still trying to measure. And all of this motion is happening simultaneously, layered on top of each other, creating a velocity so complex that physicists need supercomputers just to calculate where you'll be in 1,000 years. You are not still. You have never been still. You are a passenger on a cosmic journey that began 13.8 billion years ago and has no destination. But here's what I want you to understand. For your entire existence, you've been alone. Alone in the sense that, as far as we know, no other conscious being in the universe has ever looked up at the night sky and wondered about their place in it. No other civilization has ever built telescopes. No other species has ever asked the question that defines our species. Are we alone? For centuries, that question was purely philosophical. We could only wonder. We could only imagine. We could only dream of what might exist in the vast darkness beyond our world. But in the last 30 years, something extraordinary has happened. We've developed the technology to actually search for an answer. We've built telescopes so powerful they can see light from planets orbiting distant stars. We've learned to read the chemical fingerprints of alien atmospheres. We've developed the ability to detect the signatures of life itself, written in the molecules that surround other worlds. And on August 29, 2024, we found something that changed everything. Scientists announced the detection of a molecule called dimethyl sulfide, DMS, in the atmosphere of an exoplanet called K2-18b. On Earth, this molecule is produced almost exclusively by living organisms. It's the smell of rotting seaweed. It's the odor released by phytoplankton in our oceans. It's a biosignature, a sign of life, and it was found 120 light years away, orbiting a star we can't even see with our naked eyes. The statistical confidence in this detection is 99.7%. That means there's only a 0.3% chance this is a false alarm. In scientific terms, that's approaching what we call a 5 sigma detection, which is the gold standard for claiming discovery of something revolutionary. For the first time in human history, we have evidence, real, measurable, scientifically rigorous evidence, that life exists beyond Earth. But here's what makes this story so much more complex than a simple, "we found aliens" headline. Because the evidence is not yet conclusive. Because there are alternative explanations. Because the universe, as it always does, is more complicated than we want it to be. This is the story of K2-18b. This is the story of how we searched for life among the stars. And this is the story of what we found when we finally looked in the right place. To understand why the detection of DMS on K2-18b is so significant, we need to go back to the beginning. We need to understand how we got here. How we went from wondering if life exists elsewhere to actually being able to detect it. The search for extraterrestrial life is not new. In 1961, an astronomer named Frank Drake created what's known as the Drake equation. It's a mathematical formula designed to estimate the number of communicative civilizations in our galaxy. The equation looks like this. N equals R asterisk times Fp times Ne times Fl times Phi times Fc times L. Don't let the symbols intimidate you. What Drake was trying to do was break down the question, how many alien civilizations are out there, into smaller, more manageable questions. Our asterisk is the rate at which stars form in the galaxy. We can measure this. We know roughly how many stars are born each year. Fp is the fraction of those stars that have planets. For most of human history, we didn't know if any stars had planets. We assumed they did, but we had no proof. Now we know that planets are incredibly common. Most stars have them. Ne is the number of habitable planets per star system. Some systems might have one, some might have many. Fl is the fraction of habitable planets where life actually emerges. This is where things get speculative. We only have one example, Earth. So we don't really know how common life is. Phi is the fraction of life-bearing planets where intelligent life develops. Again, one example. We don't know. Fc is the fraction of intelligent civilizations that develop technology and communicate across space. And L is the length of time such civilizations survive. When Drake plugged in his estimates in 1961, he came up with a number that shocked people. Somewhere between 1,000 and 100 million communicative civilizations in our galaxy alone. But here's the problem. We've been listening for signals from space since the 1960s. We've pointed our radio telescopes at the stars, searching for any sign of artificial transmission. And we've found nothing. Nothing at all. This is what's known as the Fermi paradox, named after physicist Enrico Fermi. If there are so many civilizations out there, where is everybody? Why haven't we detected any signals? Why haven't they visited us? Why is the universe so quiet? There are many possible explanations. Maybe intelligent life is rarer than we think. Maybe civilizations don't last very long. They destroy themselves before they can spread across the stars. Maybe they're out there, but they're not broadcasting in ways we can detect. Maybe they're deliberately avoiding contact with us. Or maybe, just maybe, we've been looking in the wrong way. For decades, the search for extraterrestrial intelligence focused on radio signals. We assumed that if aliens existed, they would be technological beings like us, capable of sending messages across space. But what if we're wrong? What if life exists on other worlds, but it's not intelligent? What if it's microbial? What if it's simple organisms living in the oceans of distant planets? That question led to a new approach. Instead of listening for signals, we started looking for biosignatures. Chemical signatures that indicate the presence of life. On Earth, life has fundamentally altered our atmosphere. The oxygen we breathe is almost entirely produced by living organisms. 3 billion years ago, our atmosphere had almost no oxygen. Then photosynthetic bacteria evolved, and they began converting carbon dioxide and water into oxygen and sugar. This was called the Great Oxidation Event, and it transformed our planet. Today, oxygen makes up 21% of Earth's atmosphere. If an alien scientist pointed a telescope at Earth and analyzed our atmosphere, they would immediately see oxygen and think, something is alive down there. Because oxygen is highly reactive. It should combine with other elements and disappear from the atmosphere. The only reason we have so much of it is because life keeps producing it. But oxygen isn't the only biosignature. There are others. Methane, produced by bacteria in our soil and oceans. Nitrous oxide, produced by microbes in our soil. And dimethyl sulfide, produced by phytoplankton in our oceans. These are called biosignatures because they're signs of life. They're molecules that are produced by living organisms in quantities that would be hard to explain through non-biological processes alone. The idea of detecting biosignatures on exoplanets, planets orbiting other stars, seemed like science fiction for most of human history. We didn't even know exoplanets existed until 1992. The first exoplanet orbiting a sun-like star wasn't discovered until 1995. That's less than 30 years ago. But technology advances quickly. And in the last decade, we've developed telescopes so powerful that they can actually analyze the light passing through an exoplanet's atmosphere and determine what chemicals are present. The most important of these telescopes is the James Webb Space Telescope, which launched on Christmas Day 2021 and began operations in 2022. James Webb observes primarily in infrared, which is perfect for studying exoplanet atmospheres because many biosignatures absorb infrared light in distinctive ways. When light from a star passes through an exoplanet's atmosphere, the atmosphere absorbs certain wavelengths of light. Different molecules absorb different wavelengths. Oxygen absorbs light at specific infrared wavelengths. Methane absorbs light at different wavelengths. And dimethyl sulfide absorbs light at yet other wavelengths. By analyzing the light that reaches us from a distant star after it's passed through an exoplanet's atmosphere, we can determine what chemicals are present in that atmosphere. It's like reading a chemical fingerprint written in light. This technique is called transmission spectroscopy, and it's one of the most powerful tools we have for studying exoplanet atmospheres. But before we can use transmission spectroscopy to search for biosignatures, we need to know which exoplanets to study. We need to find planets that are potentially habitable. Planets that could support life. This is where K2-18b comes in. K2-18b was first discovered in 2015 using NASA's Kepler Space Telescope. The Kepler mission, which operated from 2009 to 2018, was designed to find exoplanets by looking for the tiny dips in brightness that occur when a planet passes in front of its star from our perspective. This is called the transit method, and it's one of the most successful techniques for finding exoplanets. When a planet transits its star, it blocks a tiny fraction of the star's light. For a planet the size of Earth orbiting a sun-like star, the dip in brightness is only about 0.01%. But Kepler was sensitive enough to detect these tiny dips, and it found thousands of exoplanets. K2-18b orbits a star called K2-18, which is located about 120 light-years away in the constellation Leo. To put that distance in perspective, 120 light-years is the distance light travels in 120 years at 186,000 miles per second. It's an almost incomprehensibly vast distance. If you traveled at the speed of light, it would take you 120 years to reach K2-18b. In a conventional spacecraft, it would take millions of years. K2-18 is what's called an M-dwarf or red dwarf. These are the most common type of star in the galaxy. They're smaller and cooler than our sun, and they live much longer. While our sun will live for about 10 billion years total, a red dwarf can live for hundreds of billions of years. K2-18 is about 0.4 times the mass of our sun and about half its diameter. It's much dimmer than our sun, which means its habitable zone, the region around the star where liquid water could exist on a planet's surface, is much closer to the star than Earth is to our sun. K2-18b orbits this red dwarf every 33 days. It's much closer to its star than Earth is to our sun. But because the star is so much dimmer, K2-18b receives about the same amount of energy from its star as Earth receives from our sun. This places it in the habitable zone. Now here's where K2-18b becomes truly interesting. K2-18b is not an Earth-like planet. It's not a small, rocky world like our home. Instead, K2-18b is what's called a subneptune or mini-Neptune. It's a planet with a mass of about 8.6 times Earth's mass and a radius of about 2.6 times Earth's radius. This makes K2-18b much larger than Earth, but smaller than Neptune. It's a type of planet that doesn't exist in our solar system, which is why it's so fascinating to study. For a long time, we thought planets came in two basic varieties: small, rocky planets like Earth, Mercury, Venus, and Mars, and large, gaseous planets like Jupiter, Saturn, Uranus, and Neptune. But when we started discovering exoplanets, we found that mini-Neptunes are actually very common. In fact, they might be the most common type of planet in the galaxy. This was surprising because we didn't expect mini-Neptunes to exist. Our models of planetary formation suggested that planets should either be small and rocky or large and gaseous. There shouldn't be a middle ground. But there is. And K2-18b is one of these middle ground planets. Now the question becomes, can a mini-Neptune be habitable? Can it support life? For most of human history, we assumed that habitable planets had to be like Earth. Rocky surfaces, liquid water oceans, atmospheres made mostly of nitrogen and oxygen. But as we've learned more about the diversity of exoplanets, we've realized that habitability might be more flexible than we thought. In 2021, an astronomer named Nick Madhusudhan published a paper proposing a new type of habitable world. He called it a Hycean world. Hycean is a portmanteau of hydrogen and ocean. The idea is that a mini-Neptune with a thick hydrogen-rich atmosphere could have a warm ocean beneath that atmosphere. The planet would be too large to be a traditional Earth-like world, but it could still be habitable. Here's how it would work. A mini-Neptune has a thick atmosphere made mostly of hydrogen and helium, left over from when the planet formed. This thick atmosphere would create a strong greenhouse effect, trapping heat from the star. The surface of the planet would be warm enough for liquid water to exist. Beneath the thick atmosphere, there could be a layer of liquid water, an ocean. This ocean could be kept warm by the greenhouse effect of the atmosphere above and by heat from the planet's interior. And in this warm ocean, life could potentially exist. This is not a traditional habitable zone planet like Earth. It's something different, something we've never seen before. But it could work. K2-18b is a candidate Hycean world. It has a thick atmosphere, likely made of hydrogen and helium. It orbits in the habitable zone of its star, and it could potentially have a warm ocean beneath its atmosphere. But we didn't know this for certain. We needed to study K2-18b's atmosphere more carefully. We needed to use transmission spectroscopy to analyze what chemicals were present in its atmosphere. And that's where the James Webb Space Telescope came in. In 2023, a team of astronomers led by Nick Madhusudhan used the James Webb Space Telescope to observe K2-18b as it passed in front of its star. They used transmission spectroscopy to analyze the light passing through K2-18b's atmosphere. What they found was remarkable. The atmosphere of K2-18b contains methane, CH4, carbon dioxide, CO2, and water vapor, H2O. These are all molecules that could be produced by life. But the most significant finding came later, in 2024, when an even more detailed analysis of the James Webb data revealed something extraordinary. Dimethyl sulfide, DMS. Let me explain why this is so important. On Earth, dimethyl sulfide is produced almost exclusively by living organisms. The primary source is phytoplankton, microscopic algae that live in our oceans. These organisms produce DMS as part of their metabolism. When they die and decompose, DMS is released into the atmosphere. DMS is also produced by some bacteria in soil and by certain plants, but the vast majority of DMS in Earth's atmosphere comes from ocean phytoplankton. And here's the crucial part. DMS is produced in such large quantities by life that it's become a major component of Earth's sulfur cycle. The sulfur cycle is the process by which sulfur moves through the environment. Sulfur is an essential element for life. It's a component of amino acids, the building blocks of proteins. It's found in many other biological molecules. And when organisms die and decompose, the sulfur in their bodies is released back into the environment. On Earth, about 90% of the sulfur released into the atmosphere comes from biological sources. Most of that is DMS from ocean phytoplankton. The remaining 10% comes from volcanic activity and other geological processes. Now here's the key point. DMS is unstable in the atmosphere. It reacts with other molecules and breaks down relatively quickly. So if you detect DMS in an atmosphere, it means it's being produced continuously. It's not a leftover from some ancient biological process. It's being made right now. This makes DMS an excellent biosignature. If you detect DMS in an exoplanet's atmosphere, it's strong evidence that life is present on that planet right now. But there's a catch. DMS can also be produced through non-biological processes. Certain types of volcanic activity can produce DMS. And there are photochemical reactions driven by ultraviolet light from the star, that could potentially produce DMS without life being involved. So when the team announced the detection of DMS on K2-18b, they were careful to note that this is not definitive proof of life. It's evidence, strong evidence, but not proof. The statistical confidence in the detection was 99.7%. This means that if you repeated the observation 1,000 times, you would expect to see this signal 997 times. Only 3 times would it be a false alarm due to random noise in the data. But 99.7% confidence is not the same as certainty. In science, we use a standard called sigma to measure confidence. 1 sigma means 68% confidence. 2 sigma means 95% confidence. 3 sigma means 99.7% confidence. 4 sigma means 99.99% confidence. And 5 sigma means 99.9999% confidence. 5 sigma is the gold standard in physics. When the Higgs boson was discovered in 2012, it was a 5 sigma detection. When gravitational waves were detected in 2015, it was a 5 sigma detection. These are the discoveries that change our understanding of physics. The DMS detection on K2-18b is currently at about 3 sigma. It's very strong evidence, but it's not yet at the 5 sigma level that would constitute definitive proof. To reach 5 sigma, the team would need to make additional observations. They would need to confirm the signal using different instruments. They would need to rule out alternative explanations. And they would need to accumulate enough data that the statistical confidence becomes overwhelming. But even at 3 sigma, this is extraordinary. This is the first time we've detected a potential biosignature on an exoplanet. This is the first time we've found evidence that life might exist beyond Earth. Let me walk you through exactly what the team observed and how they came to this conclusion. When K2-18b passes in front of its star, the star's light passes through K2-18b's atmosphere before reaching us. Different molecules in the atmosphere absorb light at different wavelengths. By analyzing the light that reaches us, we can determine what molecules are present. The team used James Webb's infrared spectrograph to measure the light passing through K2-18b's atmosphere across a range of infrared wavelengths. They looked for absorption features, dips in the light intensity, that would indicate the presence of specific molecules. They found clear evidence of methane and water vapor, which had been detected in previous observations. But when they looked more carefully at the data, they found something new. A subtle absorption feature that matched the signature of dimethyl sulfide. Now, here's where it gets tricky. The signal was subtle. It wasn't overwhelming. It required careful analysis to extract it from the data, and there were other possible explanations for the signal. The team had to rule out these alternative explanations. They had to show that DMS was the best explanation for what they observed. One alternative explanation was that the signal was caused by sulfur dioxide, SO2, another sulfur-containing molecule. Sulfur dioxide can be produced by volcanic activity. But when the team analyzed the data, they found that the wavelengths of the absorption feature matched DMS better than SO2. The signal was more consistent with DMS. Another alternative explanation was that the signal was caused by photochemistry. Ultraviolet light from the star could potentially drive chemical reactions that produce sulfur-containing molecules. But the team calculated that the amount of DMS that could be produced through photochemistry alone was far too small to explain the observed signal. The amount of DMS detected was much larger than photochemistry could produce. So the team concluded that the most likely explanation for the observed signal was the presence of DMS in K2-18b's atmosphere. And if DMS is present, the most likely source is life. But they were careful to note that this is not definitive proof. It's strong evidence. It's a biosignature detection. But it's not proof of life. Why the caution? Because in science, we have to be careful about jumping to conclusions. We have to consider alternative explanations. We have to be rigorous and skeptical. And there are still questions about K2-18b that we can't answer yet. To truly understand why the detection of DMS on K2-18b is so significant, we need to understand what DMS is, where it comes from, and why it's such a powerful biosignature. Dimethyl sulfide is a small molecule made of 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom. The chemical formula is C2H6S. It's a volatile compound, meaning it evaporates easily at room temperature. On Earth, it has a distinctive smell, the smell of rotting seaweed, or the smell of the ocean after a storm. If you've ever walked along a beach and smelled that pungent, slightly unpleasant odor, you've smelled dimethyl sulfide. That smell is produced by billions of tons of DMS being released from the ocean into the atmosphere every year. The primary source of DMS on Earth is phytoplankton. Phytoplankton are microscopic algae that live in the ocean. They're the base of the marine food chain. They're responsible for producing about half of the oxygen in Earth's atmosphere, and they produce enormous quantities of DMS. But why do phytoplankton produce DMS? What's the purpose? Scientists believe that DMS is produced as a byproduct of the metabolism of a compound called dimethyl sulfonylpropionate, or DMSP. DMSP is produced by phytoplankton as an osmolyte, a molecule that helps regulate the water content inside the cell. When the cell breaks down DMSP, DMS is released. So DMS is essentially a waste product of phytoplankton metabolism. It's not intentionally produced for any particular purpose. It's just a byproduct that gets released into the atmosphere. But here's what's remarkable. Even though DMS is just a waste product, it plays a crucial role in Earth's climate system. When DMS is released from the ocean, it rises into the atmosphere. In the atmosphere, DMS is oxidized by hydroxyl radicals and other reactive molecules. This oxidation process converts DMS into sulfur dioxide and other sulfur-containing compounds. These compounds then condense into tiny particles called sulfate aerosols. Sulfate aerosols are important because they reflect sunlight back into space. They have a cooling effect on Earth's climate. They also serve as cloud condensation nuclei, particles around which water vapor can condense to form clouds. Clouds also reflect sunlight and have a cooling effect. So the DMS produced by ocean phytoplankton influences Earth's climate. It helps regulate how much sunlight reaches Earth's surface. This is called the claw hypothesis, named after the scientists who proposed it: Charlson, Lovelock, Andrea, and Warren. The claw hypothesis suggests that there's a feedback loop between ocean phytoplankton and Earth's climate. When Earth gets warmer, the ocean warms up and phytoplankton produce more DMS. The increased DMS leads to more sulfate aerosols and clouds, which cool the planet. When Earth gets cooler, the opposite happens. Phytoplankton produce less DMS, fewer clouds form, and the planet warms up. This feedback loop helps keep Earth's climate stable. It's one of the ways that life influences the environment and helps maintain conditions suitable for life. It's a form of planetary self-regulation. Now, here's why DMS is such an excellent biosignature. First, DMS is produced almost exclusively by life. On Earth, about 90% of atmospheric DMS comes from biological sources. The remaining 10% comes from volcanic activity and other geological processes. But the biological sources are so dominant that if you detect DMS in an atmosphere, it's strong evidence that life is present. Second, DMS is unstable. It doesn't persist in the atmosphere for very long. It reacts with other molecules and breaks down within days or weeks. So if you detect DMS, it means it's being produced right now. It's not a leftover from some ancient biological process. It's being made continuously. Third, DMS is produced in large quantities by life. On Earth, billions of tons of DMS are released into the atmosphere every year. This makes it detectable with our current technology. We can actually measure it in exoplanet atmospheres. Fourth, DMS is difficult to produce through non-biological processes. While volcanic activity can produce some DMS, the amount is small compared to what life produces. And photochemical reactions can produce some DMS, but again, the amount is small. To produce the large quantities of DMS that we would expect from a biologically active ocean world, you need life. So DMS is what's called a robust biosignature. It's a molecule that strongly indicates the presence of life. But here's the important caveat. DMS is not a false positive-free biosignature. There are non-biological processes that can produce DMS. Volcanism can produce it. Photochemistry can produce it. So detecting DMS doesn't absolutely prove that life is present. It's evidence, strong evidence, but not proof. This is why the team was careful to say that the DMS detection on K2-18b is a biosignature detection, not a detection of life itself. They're saying, we found a molecule that is strongly associated with life on Earth. We found it on K2-18b. This is evidence that life might be present on K2-18b. But they're not saying, we found life on K2-18b. That would be premature. That would be jumping to conclusions. To definitively prove that life exists on K2-18b, we would need additional evidence. We would need to detect multiple biosignatures. We would need to rule out all non-biological explanations. We would need to reach that 5 sigma level of statistical confidence. But we're getting closer, and the DMS detection is a huge step in that direction. Now let's talk about the skepticism, because in science, healthy skepticism is essential. We should question extraordinary claims. We should demand rigorous evidence, and we should consider alternative explanations. When the team announced the detection of DMS on K2-18b, not everyone was convinced. Some scientists raised important questions. Some proposed alternative explanations. And these criticisms are valid. They're important. They're part of the scientific process. Let me walk you through the main counterarguments and why they matter. The first counterargument is about volcanism. Volcanic activity on Earth produces sulfur dioxide, which can be converted into other sulfur compounds, including DMS. If K2-18b has active volcanoes, could they be producing the DMS that we detected? This is a legitimate question. We know that K2-18b is a mini Neptune with a thick atmosphere. We don't know what's beneath that atmosphere. There could be a rocky surface with volcanoes, or there could be a liquid ocean. We don't have enough information to say for certain. But here's what we do know. The amount of DMS detected on K2-18b is quite large. It's comparable to the amount of DMS in Earth's atmosphere. On Earth, volcanism produces only about 10% of the atmospheric DMS. The other 90% comes from biological sources. For volcanism alone to produce the amount of DMS detected on K2-18b, K2-18b would need to have volcanic activity that's about 10 times more intense than Earth's. That's possible, but it seems unlikely. It would require K2-18b to be a very volcanically active world. Moreover, the team found evidence of other molecules in K2-18b's atmosphere that are consistent with a biologically active ocean. Methane, for example, can be produced by methanogenic bacteria in ocean sediments. Water vapor is consistent with a warm ocean. The combination of these molecules paints a picture that's more consistent with a biologically active world than with a volcanically active world. So while volcanism is a possible explanation for some of the DMS, it's unlikely to be the primary source. The second counterargument is about photochemistry. Ultraviolet light from the star can drive chemical reactions in the atmosphere. Could these photochemical reactions be producing the DMS? Again, this is a legitimate question. Photochemistry is a real process. It happens on Earth. It happens on other planets. It could happen on K2-18b. But the team calculated how much DMS could be produced through photochemistry alone. They ran models of K2-18b's atmosphere, assuming no biological activity, and calculated what the photochemical production of DMS would be. The result was clear. Photochemistry alone could not produce enough DMS to explain the observed signal. The amount of DMS detected was much larger than photochemistry could produce. In fact, the team found that photochemistry would produce only about 1% of the DMS that was actually detected. To explain the observed signal through photochemistry alone, you would need photochemical processes that are about 100 times more efficient than our models predict. That's possible, but it seems unlikely. It would require us to have fundamentally misunderstood how photochemistry works in exoplanet atmospheres. So while photochemistry might contribute some DMS to K2-18b's atmosphere, it's unlikely to be the primary source. The third counterargument is about measurement uncertainty. How confident are we that the DMS signal is real? Could it be a false alarm? Could it be noise in the data? This is an important question. The signal is subtle. It requires careful analysis to extract it from the data, and there's always the possibility that we're seeing noise rather than a real signal. But the team addressed this by calculating the statistical significance of the detection. They found that the signal has a confidence level of 99.7%. This means that if you repeated the observation 1,000 times, you would expect to see this signal 997 times. Only 3 times would it be a false alarm due to random noise. That's very strong evidence that the signal is real. It's not a false alarm. It's not noise. It's a real detection of DMS in K2-18b's atmosphere. However, 99.7% confidence is not the same as absolute certainty. There's still a 0.3% chance that this is a false alarm. And in science, we usually want to reach 5 sigma confidence before claiming a definitive discovery. The DMS detection on K2-18b is currently at about 3 sigma, which is very strong but not quite at the 5 sigma level. The fourth counterargument is about the nature of K2-18b itself. We're assuming that K2-18b has a warm ocean beneath its thick atmosphere. But what if we're wrong? What if K2-18b is a completely different type of world than we think? This is a valid concern. We don't have direct observations of K2-18b's surface. We only know about its atmosphere. We're inferring the existence of an ocean based on models and assumptions. But the evidence supports the idea that K2-18b has a warm ocean. The presence of water vapor in the atmosphere is consistent with a warm ocean. The presence of methane is consistent with a biologically active ocean. The presence of carbon dioxide is consistent with an ocean with dissolved CO2. Moreover, the theoretical models of Hycean worlds suggest that mini-Neptunes in the habitable zone should have warm oceans beneath their thick atmospheres. K2-18b fits this model well. So while we can't be 100% certain that K2-18b has an ocean, the evidence strongly suggests that it does. The fifth counterargument is about the possibility of false positives. Even if DMS is a good biosignature on Earth, could it be produced through non-biological processes on other worlds that we haven't thought of? This is a profound question. It gets at the heart of what we mean by a biosignature. A biosignature is a molecule that we associate with life. But that association is based on our experience with Earth. On other worlds, with different chemistry, different physics, different conditions, things might be different. For example, on Earth, oxygen is a biosignature because it's produced almost exclusively by life. But on other worlds, oxygen might be produced through non-biological processes. On Venus, for example, there are chemical reactions that produce small amounts of oxygen without any biological activity. Similarly, DMS is a biosignature on Earth because it's produced almost exclusively by life. But on other worlds, there might be non-biological processes that produce DMS that we haven't thought of. There might be exotic chemistry that we don't understand. This is why scientists talk about context-dependent biosignatures. A molecule is a biosignature only in a particular context. On Earth, DMS is a biosignature. On K2-18b, we're assuming it's a biosignature, but we should be open to the possibility that we're wrong. This is why the team was careful to say that the DMS detection is evidence of a potential biosignature, not definitive proof of life. They're saying, based on what we know about Earth, this molecule is associated with life. We found it on K2-18b. This suggests that life might be present, but we should be cautious. We should consider alternative explanations. We should gather more evidence. This is good science. This is the right approach. Now, let's dig deeper into the alternative explanations. Let's explore what it would take for volcanism or photochemistry to produce the amount of DMS detected on K2-18b. First, let's talk about volcanism in more detail. On Earth, volcanic activity produces sulfur dioxide, SO2. When SO2 is released into the atmosphere, it can be converted into other sulfur compounds through chemical reactions. Some of these reactions can produce DMS, but the efficiency of this process is low. On Earth, volcanism produces only about 10% of the atmospheric DMS. The other 90% comes from biological sources. For volcanism to produce the amount of DMS detected on K2-18b, K2-18b would need to have volcanic activity that's about 10 times more intense than Earth's. But how intense is Earth's volcanic activity? On Earth, there are about 50 to 70 active volcanoes at any given time. Thousands of volcanoes have erupted in recorded history. The largest eruptions can inject millions of tons of SO2 into the atmosphere. But these are rare events. Most volcanic activity is relatively modest. If K2-18b had volcanic activity 10 times more intense than Earth's, it would need to have hundreds of active volcanoes at any given time. It would need to be a world of constant, intense volcanic activity. It would need to be more volcanically active than any planet in our solar system. Is this possible? Sure. We don't know what's happening on K2-18b. It could be a volcanically active world, but it seems unlikely, and it would require us to assume that K2-18b is an extreme world, very different from anything we see in our solar system. Moreover, intense volcanic activity would have other effects on K2-18b's atmosphere. It would produce large amounts of SO2, which would be visible in the atmosphere. It would produce ash and other particles. It would create a harsh, toxic atmosphere, but the observations of K2-18b don't show signs of intense volcanic activity. The atmosphere appears relatively stable. The presence of water vapor and methane suggests a more benign environment. So while volcanism is a possible explanation for some of the DMS, it's unlikely to be the primary source. Now let's talk about photochemistry in more detail. Photochemistry is the study of chemical reactions driven by light. On Earth, ultraviolet light from the sun drives many chemical reactions in the atmosphere. These reactions produce ozone, nitrogen oxides, and many other compounds. On K2-18b, ultraviolet light from the star could drive similar reactions. In principle, these reactions could produce DMS. But how much DMS could be produced through photochemistry? The team ran detailed models of K2-18b's atmosphere, including all the known photochemical reactions. They calculated how much DMS would be produced through these reactions. The result was surprising. Photochemistry would produce only about 1% of the DMS that was actually detected. But wait, could there be photochemical reactions that we don't know about? Could there be exotic chemistry happening on K2-18b that we haven't thought of? This is possible. Our understanding of atmospheric chemistry is based on what we see on Earth and in our solar system. On other worlds, with different conditions, there might be chemistry that we don't understand. But here's the thing. For photochemistry to produce the amount of DMS detected on K2-18b, we would need photochemical processes that are about 100 times more efficient than our models predict. That's a huge difference. It would require us to have fundamentally misunderstood how photochemistry works. Is that possible? Sure. Science is always open to the possibility that we're wrong. But it seems unlikely. Our models of photochemistry are based on well-understood physics and chemistry. They've been tested and validated on Earth and in our solar system. It would be surprising if they were off by a factor of 100. So while photochemistry might contribute some DMS to K2-18b's atmosphere, it's unlikely to be the primary source. Now let's think about what this means. If volcanism can't explain the DMS, and photochemistry can't explain the DMS, what's left? Life. That's the most straightforward explanation. On Earth, life produces the vast majority of atmospheric DMS. If K2-18b has a biologically active ocean, similar to Earth's oceans, then life could produce the DMS that we detected. But here's the important point. We're not saying that life is the only possible explanation. We're saying that life is the most likely explanation, given what we know. In science, we use something called Occam's razor. It's the principle that the simplest explanation is usually the best one. If you have multiple explanations for an observation, you should prefer the one that makes the fewest assumptions. In this case, the simplest explanation is that DMS is being produced by life on K2-18b. This requires only one assumption, that life exists on K2-18b. The alternative explanations require multiple assumptions, that K2-18b has intense volcanic activity, or that photochemistry is 100 times more efficient than we think, or that there's some other exotic process we haven't thought of. So by Occam's razor, life is the most likely explanation. But we should still be cautious. We should still consider the alternatives. We should still gather more evidence. Now let's imagine what K2-18b is actually like. Let's try to visualize this world 120 light-years away. K2-18b orbits a red dwarf star called K2-18. This star is much dimmer than our Sun, so K2-18b orbits very close to its star. The orbital period is only 33 days. This means K2-18b completes one orbit around its star in just 33 days. For comparison, Earth takes 365 days to orbit the Sun. Because K2-18b orbits so close to its star, one side of the planet is always facing the star. This is called tidal locking. It's the same reason that the Moon always shows the same face to Earth. The gravitational pull of the star has locked K2-18b's rotation, so that one side always faces the star, and the other side always faces away. This means that K2-18b has a day side and a night side. The day side is always facing the star and always receiving starlight. The night side is always facing away from the star and is always in darkness. On the day side, the temperature is warm. How warm? We don't know exactly, but models suggest it could be anywhere from 50 degrees Celsius to 200 degrees Celsius, depending on the atmospheric circulation and other factors. That's hot, but not impossibly hot. It's hotter than Earth's surface, but cooler than Venus. On the night side, the temperature is much cooler. Without any starlight, the night side radiates heat into space. The temperature could drop to minus 50 degrees Celsius or lower. Between the day side and the night side, there's a terminator line, the boundary between day and night. This is where the most interesting things might be happening. This is where the temperature is moderate. This is where life might thrive. K2-18b has a thick atmosphere made mostly of hydrogen and helium. This atmosphere is much thicker than Earth's atmosphere. It's more like the atmosphere of Neptune or Uranus, but warmer. This thick atmosphere creates a strong greenhouse effect. The hydrogen and helium don't directly trap heat the way that carbon dioxide or methane do, but they do affect how heat is distributed in the atmosphere. They help keep the planet warm. Beneath this thick atmosphere, there's likely a layer of liquid water, an ocean. This ocean could be hundreds of kilometers deep. It could be warm, kept warm by the greenhouse effect of the atmosphere above and by heat from the planet's interior. In this warm ocean, life could potentially exist. Microorganisms could thrive in the water. They could produce DMS as a byproduct of their metabolism. The DMS would rise into the atmosphere, where we could detect it with our telescopes. But what would this life be like? Would it be similar to Earth life? Or would it be completely different? This is one of the most fascinating questions in astrobiology. We only have one example of life, Earth life, so we don't know how universal the principles of life are. We don't know if life on other worlds would be similar to Earth life or radically different. But we can make some educated guesses based on what we know about chemistry and physics. First, any life on K2-18b would almost certainly be based on chemistry. Life requires chemistry. It requires molecules that can interact with each other, that can store information, that can replicate. The most likely chemistry for life is carbon chemistry, because carbon is so versatile. It can form long chains and complex structures that are ideal for life. So K2-18b life would probably be carbon-based, like Earth life. Second, any life on K2-18b would need a solvent. On Earth, the solvent is water. Water is an excellent solvent for life because it can dissolve many different molecules and allow them to interact. It's also abundant in the universe. On K2-18b, the solvent would probably be water, like on Earth. But it could potentially be something else. On Saturn's moon Titan, for example, there might be life based on liquid methane instead of water. But water is the most likely solvent. Third, any life on K2-18b would need to be able to extract energy from its environment. On Earth, life does this through various means. Photosynthetic organisms extract energy from sunlight. Chemosynthetic organisms extract energy from chemical reactions. Heterotrophic organisms extract energy by eating other organisms. On K2-18b, life would need to extract energy somehow. If there's photosynthetic life, it would use the light from the star. If there's chemosynthetic life, it would use chemical energy from the ocean. The most likely scenario is that there's a combination of both. Fourth, any life on K2-18b would need to be able to reproduce. On Earth, life reproduces through various means. Asexual reproduction, sexual reproduction, binary fission. The key requirement is that organisms can pass on their genetic information to offspring. On K2-18b, life would need to reproduce somehow. The most likely mechanism would be similar to Earth life, with organisms having some kind of genetic material that can be copied and passed on. So based on these principles, we can imagine what K2-18b life might be like. At the bottom of the ocean, near hydrothermal vents, there might be chemosynthetic bacteria. These organisms would extract energy from chemical reactions, just like the chemosynthetic bacteria in Earth's deep oceans. They would form the base of the food chain. Higher up in the ocean, there might be photosynthetic organisms, similar to Earth's phytoplankton. These organisms would use the light from the star to produce energy through photosynthesis. They would produce oxygen as a byproduct, just like Earth's phytoplankton. These photosynthetic organisms would produce DMS as a byproduct of their metabolism. The DMS would rise into the atmosphere, where we could detect it with our telescopes. Higher up in the food chain, there might be larger organisms that eat the photosynthetic organisms. These could be simple multicellular organisms, similar to Earth's zooplankton. Or they could be more complex organisms. The entire ecosystem would be similar to Earth's ocean ecosystem, but adapted to the conditions on K2-18b. The organisms would be adapted to the warm water, the high pressure, the different chemistry. But here's the important point. This is all speculation. We don't know if life on K2-18b would actually be like this. We're basing our speculation on Earth life, but life on K2-18b could be completely different. It could be based on different chemistry. It could use different energy sources. It could have a completely different structure. The only thing we can say with confidence is that if life exists on K2-18b, it would need to follow the laws of chemistry and physics. It would need to extract energy from its environment. It would need to reproduce. It would need to be adapted to the conditions on K2-18b. Beyond that, we're just guessing. Now let's step back and think about the bigger picture. Why does the detection of DMS on K2-18b matter so much? Why is this such a significant discovery? The answer is simple. For the first time in human history, we have evidence that life might exist beyond Earth. This is profound. This changes everything. For thousands of years, humans have wondered if we're alone in the universe. We've asked the question, are we unique? Is Earth the only world with life? Or is life common throughout the cosmos? For most of human history, we had no way to answer this question. We could only speculate. We could only imagine. But now, with the James Webb Space Telescope and other advanced instruments, we can actually search for answers. We can analyze the atmospheres of distant planets. We can look for biosignatures. We can search for evidence of life. And we found something. We found DMS on K2-18b. We found a molecule that, on Earth, is produced almost exclusively by life. We found it on a planet 120 light-years away. This is not definitive proof that life exists on K2-18b, but it's strong evidence. It's a biosignature detection. It's the first time we've found such evidence, and this has profound implications. First, it suggests that life might be common in the universe. If we found evidence of life on one of the first exoplanets we looked at carefully, maybe life is not rare. Maybe it's common. Maybe there are billions of planets with life. Second, it suggests that life might exist in environments very different from Earth. K2-18b is a mini Neptune with a thick atmosphere and a warm ocean. It's very different from Earth. If life can exist on K2-18b, maybe it can exist in many different environments. Maybe life is more adaptable than we thought. Third, it suggests that we're not alone. For the first time, we have evidence that we might not be the only conscious beings in the universe. There might be other life out there. Maybe not intelligent life. Maybe just microorganisms. But life nonetheless. This is a profound realization. It changes how we see ourselves. It changes our place in the cosmos. For most of human history, we thought we were special. We thought Earth was the center of the universe. We thought we were unique. But science has gradually shown us that we're not special. We're not at the center. We're just one planet among billions. The discovery of life on K2-18b would be the final step in this realization. It would show us that we're not unique. Life is not unique to Earth. Life is part of the fabric of the universe. But there's more. The detection of DMS on K2-18b also has implications for our understanding of how life emerges. On Earth, life emerged relatively quickly. The earliest evidence of life dates back about 3.8 billion years, which is only about 700 million years after Earth formed. This suggests that life can emerge fairly quickly, given the right conditions. If life exists on K2-18b, it would suggest that life can emerge on many different worlds, in many different environments. It would suggest that the emergence of life is not a rare, special event. It's something that happens naturally when the conditions are right. This would have implications for the Drake equation, which I mentioned earlier. Remember, the Drake equation tries to estimate the number of communicative civilizations in the galaxy. One of the key terms in the equation is FL, the fraction of habitable planets where life actually emerges. For most of human history, we didn't know what FL was. We only had one example, Earth. So we had to guess. Some scientists thought FL was very small, maybe 0.01 or 0.001. Others thought it was close to 1, meaning that life emerges on almost every habitable planet. But now, if we have evidence that life exists on K2-18b, we have a second data point. We have two examples of life. This doesn't give us a definitive answer, but it gives us more information. If life exists on both Earth and K2-18b, and if these are just two of the first planets we looked at carefully, then maybe life is common. Maybe FL is close to 1. Maybe life emerges on most habitable planets. If that's true, then the Drake equation suggests that there are many, many civilizations in the galaxy. Maybe millions, maybe billions. Of course, this is still speculation. We need more data. We need to find life on other planets. We need to build up a statistical sample. But the discovery of DMS on K2-18b is a start. So what happens next? How do we move forward from here? The first step is to confirm the DMS detection on K2-18b. We need to make additional observations using different instruments and different methods. We need to rule out instrumental artifacts and systematic errors. We need to reach that 5 sigma level of statistical confidence. The James Webb Space Telescope will continue to observe K2-18b. Additional observations will provide more data, allowing the team to refine their analysis and increase the statistical confidence in the DMS detection. But there are also other telescopes that can help. The upcoming extremely large telescope, which is currently under construction in Chile, will be even more powerful than James Webb. It will be able to detect biosignatures on exoplanets with even greater precision. The Habitable Worlds Observatory, which is being planned by NASA, will be specifically designed to search for biosignatures on exoplanets. It will be able to analyze the atmospheres of dozens of potentially habitable planets, looking for signs of life. These future telescopes will allow us to search for biosignatures on many different exoplanets. We'll be able to look for oxygen, methane, DMS, and other molecules that indicate the presence of life. But there's a challenge. Most exoplanets are too faint to analyze with current technology. We can only study the atmospheres of relatively nearby exoplanets, or exoplanets that are very large. K2-18b is relatively nearby, 120 light-years, and relatively large, 2.6 times Earth's radius, which is why we can study it. But there are many exoplanets that are farther away or smaller, and we can't study them yet. As technology improves, we'll be able to study fainter and smaller exoplanets. We'll be able to search for biosignatures on more and more worlds. Another important development is the search for other biosignatures. DMS is one biosignature, but there are others. Oxygen is a biosignature. Methane is a biosignature. Phosphine might be a biosignature. Ozone might be a biosignature. By searching for multiple biosignatures, we can increase our confidence that we've found life. If we detect DMS and oxygen and methane on the same planet, that's much stronger evidence than detecting just one biosignature. The team is already looking for other biosignatures on K2-18b. They found evidence of methane and water vapor. They're looking for other molecules. As they gather more data, they'll be able to paint a more complete picture of K2-18b's atmosphere. Another important development is the study of other potentially habitable exoplanets. K2-18b is just one of many exoplanets that might be habitable. There are thousands of known exoplanets, and many of them might be in the habitable zone of their star. Some of these exoplanets might be better candidates for biosignature detection than K2-18b. They might be closer to us. They might have thinner atmospheres that are easier to analyze. They might have different atmospheric compositions that make biosignatures easier to detect. By studying many different exoplanets, we'll increase our chances of finding life. We'll be able to build up a statistical sample. We'll be able to answer the question, how common is life in the universe? But there's also a philosophical question. What does it mean to find life on another planet? What are the implications? If we find microbial life on K2-18b or another exoplanet, that would be extraordinary. But it wouldn't necessarily mean that intelligent life exists elsewhere. Microbial life and intelligent life are very different things. On Earth, microbial life emerged relatively quickly, within a few 100 million years of Earth's formation. But intelligent life took much longer. Humans didn't emerge until about 3 billion years after life first appeared on Earth. That's a huge difference. So even if life is common in the universe, intelligent life might be rare. There might be billions of planets with microbial life, but only a handful with intelligent civilizations. But the existence of any life beyond Earth would still be profound. It would answer the question that has haunted humanity for millennia. Are we alone? The answer would be no. We are not alone. Life is not unique to Earth. Life is part of the universe. Now let's talk more about Hycean worlds, because K2-18b is a candidate Hycean world, and this represents a fundamental shift in how we think about habitability. For most of human history, when we thought about habitable planets, we thought about Earth-like planets. Rocky planets with solid surfaces, liquid water oceans, atmospheres made of nitrogen and oxygen, continents and mountains and weather. This made sense. We only had one example of a habitable planet, Earth. So we assumed that all habitable planets would be like Earth. But as we've discovered more exoplanets, we've realized that the universe is far more diverse than we imagined. There are planets much larger than Earth. There are planets much smaller than Earth. There are planets with atmospheres made of hydrogen and helium. There are planets orbiting red dwarf stars, which are very different from our Sun. And we've realized that habitability might be more flexible than we thought. In 2021, Nika Madhusudhan proposed the concept of Hycean worlds. These are mini-Neptunes with thick hydrogen-rich atmospheres and warm oceans beneath those atmospheres. Here's how a Hycean world would work. A mini-Neptune forms around a star. It has a mass of about 2 to 10 times Earth's mass. It has a thick atmosphere made mostly of hydrogen and helium, left over from when the planet formed. If this mini-Neptune orbits in the habitable zone of its star, it receives a moderate amount of energy from the star. Not too much, not too little. Just right. The thick atmosphere creates a strong greenhouse effect. The hydrogen and helium don't directly trap heat, but they do affect how heat is distributed. The atmosphere helps keep the planet warm. Beneath the thick atmosphere, there's a layer of liquid water. This ocean is warm, kept warm by the greenhouse effect of the atmosphere above and by heat from the planet's interior. In this warm ocean, life could potentially exist. The ocean would have a chemistry similar to Earth's oceans, with dissolved salts and minerals. The temperature would be moderate, warm enough for life, but not so hot that organic molecules break down. The ocean would be protected from the harsh radiation of space by the thick atmosphere above. It would be a stable, habitable environment. This is very different from Earth. Earth is a rocky planet with a thin atmosphere. K2-18b is a mini-Neptune with a thick atmosphere, but both could be habitable. Both could support life. This is a profound realization. It means that habitability is not limited to Earth-like planets. It means that many different types of planets could be habitable. It means that there are many more potentially habitable worlds than we previously thought. How many more? Well, mini-Neptunes are very common. In fact, they might be the most common type of planet in the galaxy. If a significant fraction of mini-Neptunes are in the habitable zone of their star, and if a significant fraction of those have warm oceans beneath their atmospheres, then there could be billions of Hycean worlds in the galaxy. Billions of potentially habitable worlds. Billions of places where life could exist. This is staggering. This suggests that the universe is teeming with habitable worlds. Life might be common. Very common. But there's a catch. We don't know for certain that Hycean worlds are actually habitable. We've never observed one directly. We've never confirmed that a Hycean world has a warm ocean beneath its atmosphere. K2-18b is a candidate Hycean world. The observations suggest that it might have a warm ocean. But we're not certain. To confirm that Hycean worlds are habitable, we would need to find life on one. We would need to detect biosignatures on a Hycean world. We would need to confirm that life can actually exist in these environments. And that's exactly what the DMS detection on K2-18b might represent. If the DMS is indeed produced by life, then K2-18b would be the first confirmed Hycean world with life. It would prove that Hycean worlds are habitable. This would be revolutionary. It would open up an entirely new class of potentially habitable planets. It would suggest that the universe is far more habitable than we previously thought. Now let's talk about the statistics in more detail, because understanding the statistical significance of the DMS detection is crucial to understanding what it means. The team reported that the DMS detection has a confidence level of 99.7%. This is a 3 sigma detection. But what does that mean exactly? In statistics, sigma is a measure of standard deviation. It's a way of quantifying how far a measurement is from the expected value. If you make a measurement and the result is 1 sigma away from the expected value, that means there's a 68% chance that the measurement is correct and a 32% chance that it's a false alarm due to random noise. If the result is 2 sigma away from the expected value, there's a 95% chance that the measurement is correct and a 5% chance that it's a false alarm. If the result is 3 sigma away from the expected value, there's a 99.7% chance that the measurement is correct and a 0.3% chance that it's a false alarm. If the result is 4 sigma away from the expected value, there's a 99.99% chance that the measurement is correct and a 0.01% chance that it's a false alarm. If the result is 5 sigma away from the expected value, there's a 99.9999% chance that the measurement is correct and a 0.0001% chance that it's a false alarm. 5 sigma is the gold standard in physics. When we claim that we've discovered something revolutionary, we usually require 5 sigma evidence. The DMS detection on K2-18b is currently at 3 sigma. This is very strong evidence, but it's not quite at the 5 sigma level. To reach 5 sigma, the team would need to make additional observations. They would need to accumulate more data. They would need to reduce the uncertainty in their measurements. But here's the important point. 3 sigma is already very strong evidence. It's much stronger than the evidence we usually have for most scientific claims. In fact, in many fields of science, 2 sigma is considered sufficient evidence to claim a discovery. 2 sigma means 95% confidence. That's pretty good. 3 sigma means 99.7% confidence. That's excellent. That's very strong evidence. So the DMS detection on K2-18b is already at a level of confidence that would be considered a significant discovery in most fields of science. But in physics, we're more demanding. We want 5 sigma. We want 99.9999% confidence. We want to be almost absolutely certain before we claim a revolutionary discovery. This is because in physics, we're often making claims that contradict our previous understanding of the universe. We're saying that something is true that we didn't think was true before. We want to be very, very sure before we make such a claim. So the team is being appropriately cautious. They're saying, we have very strong evidence that DMS is present in K2-18b's atmosphere. We have 99.7% confidence. But we want to reach 5 sigma before we claim definitive proof of life. This is good science. This is the right approach. But it's also important to note that 3 sigma is already very strong evidence. If you had to bet money on whether the DMS is real or a false alarm, you would bet that it's real. The odds are 999 to 1 in favor of the DMS being real. Now let's revisit the Drake equation, because the DMS detection on K2-18b has implications for how we think about the number of civilizations in the galaxy. Remember, the Drake equation is n equals r asterisk times fp times ne times fl times phi times fc times l. Each term represents a different factor that affects the number of communicative civilizations in the galaxy. Our asterisk is the rate at which stars form. We know this fairly well. It's about 1 to 3 stars per year in the Milky Way. Fp is the fraction of stars that have planets. We now know this is very high, probably close to 1. Most stars have planets. Ne is the number of habitable planets per star system. We don't know this well, but estimates range from 0.1 to 1 or more. Fl is the fraction of habitable planets where life actually emerges. This is where the DMS detection on K2-18b becomes important. Before the DMS detection, we had only one example of a habitable planet with life, Earth. So we had to guess what Fl was. Some scientists thought it was very small, maybe 0.001 or 0.01. Others thought it was close to 1. But now, if the DMS detection is confirmed, and if it's indeed evidence of life on K2-18b, we have a second example. We have 2 data points. If both Earth and K2-18b have life, and if these are just 2 of the first planets we looked at carefully, then maybe life is common. Maybe Fl is close to 1. Maybe life emerges on most habitable planets. If Fl is close to 1, then the Drake equation suggests that there are many civilizations in the galaxy. Let's plug in some numbers. Our asterisk equals 1 to 3 stars per year. Fp equals 0.9, most stars have planets. Ne equals 0.5, on average, each star system has half a habitable planet. Fl equals 0.9, if life is common. Phi equals 0.01. Intelligent life is rare, maybe 1 in 100 habitable planets. Fc equals 0.1. Communicative civilizations are rare, maybe 1 in 10 intelligent civilizations. L equals 1 million years. Civilizations last on average 1 million years. So with these assumptions, there would be about 400,000 communicative civilizations in the Milky Way galaxy. That's a lot. That's far more than we see evidence for. Of course, these are just estimates. Different scientists would plug in different numbers. But the point is that if life is common, high Fl, then the Drake equation suggests that there are many civilizations in the galaxy. But here's the problem. We don't see evidence of these civilizations. We don't detect radio signals. We don't see evidence of megastructures or space travel. The universe seems quiet. This is the Fermi paradox again. If there are so many civilizations, where is everybody? There are several possible explanations. One explanation is that intelligent life is much rarer than we think. Maybe phi is very small. Maybe intelligent life emerges on only 1 in a million habitable planets. In that case, even if life is common, intelligent life would be rare. Another explanation is that communicative civilizations are short-lived. Maybe L is very small. Maybe civilizations only last a few hundred years before they destroy themselves or lose interest in space exploration. In that case, there might be many civilizations, but they're not around long enough for us to detect them. Another explanation is that we're looking in the wrong way. Maybe civilizations don't broadcast radio signals. Maybe they communicate through methods we haven't thought of. Maybe they're deliberately avoiding contact with us. Or maybe, just maybe, we're the first. Maybe intelligent life is so rare that we're the first civilization in the galaxy. Maybe we're alone after all. The DMS detection on K2-18b doesn't resolve the Fermi paradox, but it does provide new information. It suggests that microbial life might be common, but it doesn't tell us anything about intelligent life. So the Fermi paradox remains a mystery, but it's a mystery that we can now begin to investigate more rigorously. Now let's think about the philosophical implications of the DMS detection on K2-18b. What does this mean for humanity? What does this mean for our place in the universe? For thousands of years, humans have been the center of creation. We've been special. We've been unique. We've been the pinnacle of existence. In ancient times, we thought Earth was the center of the universe. We thought the sun, moon, and stars revolved around us. We were at the center of everything. Then Copernicus came along and showed us that we were wrong. Earth orbits the sun, not the other way around. We're not at the center. We're just one planet among many. Then we realize that our sun is just one star among billions. Our galaxy is just one galaxy among billions. We're not special. We're not unique. We're just a tiny speck in an incomprehensibly vast universe. And now, with the detection of DMS on K2-18b, we're learning that life is not unique to Earth. Life is not special. Life is part of the fabric of the universe. This is a profound realization. It's a continuation of the process of cosmic humbling that began with Copernicus. But it's also a realization that brings us closer to understanding our place in the universe. We're not alone. We're part of a community of life-bearing worlds. We're part of a living universe. This has implications for how we see ourselves. It changes our perspective. It changes our values. For most of human history, we've seen ourselves as separate from nature. We've seen ourselves as above nature. We've exploited nature for our own benefit, without considering the consequences. But if we're part of a living universe, if life is common, if we're just one example among billions, then maybe we need to reconsider our relationship with nature. Maybe we need to be more respectful. Maybe we need to be more careful. The detection of life on K2-18b, if confirmed, would be a wake-up call. It would remind us that we're not special. We're not unique. We're part of something larger than ourselves. It would also raise new questions. If life exists on K2-18b, what about the billions of other potentially habitable planets? How much life is out there? How diverse is it? What forms does it take? And most importantly, if life is common, then why haven't we detected intelligent civilizations? Are we alone? Are we the first? Or are intelligent civilizations so rare that they almost never exist? These are profound questions. They're questions that will occupy scientists and philosophers for generations to come. So what happens now? What's the next step in the search for life beyond Earth? The first step is to confirm the DMS detection on K2-18b. We need more observations. We need more data. We need to reach that 5 sigma level of statistical confidence. The James Webb Space Telescope will continue to observe K2-18b. The team will analyze the data in even more detail. They'll look for other biosignatures. They'll try to rule out alternative explanations. If the DMS detection holds up, if it's confirmed by multiple observations using different instruments, then we'll have strong evidence that life exists on K2-18b. But even if the DMS detection is confirmed, we still won't have definitive proof. We'll have evidence, strong evidence, but not proof. To have definitive proof, we would need to actually visit K2-18b. We would need to send a spacecraft there. We would need to collect samples. We would need to analyze them directly. But K2-18b is 120 light-years away. Even at the speed of light, it would take 120 years to get there. In a conventional spacecraft, it would take millions of years. So direct exploration of K2-18b is not feasible with current technology. We'll have to rely on remote observations. But there are other exoplanets that might be closer. There are other potentially habitable planets that we can study. In fact, there's a planet called TRAPPIST, 1e that's only about 39 light-years away. It's an Earth-sized planet orbiting in the habitable zone of a red dwarf star. It's a good candidate for biosignature detection. There's also a planet called Proxima Centauri b, which is only 4.2 light-years away. It's a potentially habitable planet orbiting the closest star to our Sun. It's another good candidate. As we continue to discover more exoplanets, we'll have more targets to study. We'll be able to search for biosignatures on many different worlds. And as our technology improves, we'll be able to detect fainter and smaller planets. We'll be able to analyze atmospheres with greater precision. We'll be able to search for more subtle biosignatures. In the next few decades, we might find definitive evidence of life on another planet. We might find multiple examples of life. We might be able to answer the question that has haunted humanity for millennia. Are we alone? But even if we don't find life, the search itself is valuable. It teaches us about the universe. It teaches us about ourselves. It expands our perspective. The search for life beyond Earth is one of the most important scientific endeavors of our time. It's a search that will define our generation and the generations to come. Now, let me bring you back to where we started. Remember, you're traveling through space at 67,000 miles per hour. You're hurtling through the cosmos at incomprehensible speeds. You're part of a cosmic journey that began 13.8 billion years ago. And now, we know that you're not alone on this journey. Somewhere out there, 120 light-years away, there might be other life. There might be microorganisms in the warm oceans of K2-18b, producing DMS as a byproduct of their metabolism. These organisms, if they exist, would be completely unaware of us. They would have no idea that we exist. They would have no idea that we're looking for them. But we know they might be there. And that changes everything. For the first time in human history, we have evidence that life might exist beyond Earth. We have evidence that we might not be alone. This is a moment of profound significance. This is a moment that will be remembered for generations to come. The detection of DMS on K2-18b is not the end of the story. It's the beginning. It's the first step in a journey that will take us to the stars. In the coming decades, we'll search for life on other planets. We'll find more biosignatures. We'll discover more worlds with life. We'll begin to understand how common life is in the universe. And as we do, our perspective will change. We'll realize that we're not special. We're not unique. We're part of a living universe. But we'll also realize that we have a responsibility. We have a responsibility to protect our own world. We have a responsibility to preserve life on Earth. We have a responsibility to be good stewards of our planet. Because if life is common in the universe, then Earth's life is precious. It's unique. It's irreplaceable. The detection of DMS on K2-18b reminds us of this. It reminds us that we're part of something larger than ourselves. It reminds us that we're not alone. And that, perhaps, is the most important message of all. As we look to the future, astrobiology, the study of life in the universe, is becoming one of the most important fields of science. For most of human history, astrobiology was a fringe field. It was considered speculative. It was not taken seriously by mainstream science. But that's changing. With the discovery of thousands of exoplanets, with the development of powerful telescopes like James Webb, with the detection of potential biosignatures like DMS on K2-18b, astrobiology is becoming mainstream. Universities are establishing astrobiology departments. Research funding is increasing. The best minds in science are turning their attention to the question of life beyond Earth. And this is leading to new discoveries and new insights. For example, we're learning more about the conditions necessary for life. We're learning that life might be more adaptable than we thought. We're learning that life might exist in environments very different from Earth. We're also learning more about biosignatures. We're learning which molecules are good indicators of life. We're learning how to detect them in exoplanet atmospheres. And we're learning more about the diversity of exoplanets. We're learning that there are many different types of planets. Some are Earth-like, some are mini-Neptunes, some are hot Jupiters, some are super-Earths. Each type of planet presents different opportunities and challenges for life. Each type of planet might host different forms of life. As we continue to study exoplanets, we'll gain a better understanding of which planets are most likely to host life. We'll be able to prioritize our search. We'll be able to focus our efforts on the most promising targets. And as our technology improves, we'll be able to detect life on more and more planets. We'll be able to build up a statistical sample. We'll be able to answer fundamental questions about the prevalence of life in the universe. So, are we alone? Based on the detection of DMS on K2-18b, the answer seems to be no. We're probably not alone. But this is not definitive proof. This is evidence. Strong evidence. But not proof. To definitively answer the question, are we alone? We would need to find multiple examples of life on different planets. We would need to confirm biosignatures using multiple methods. We would need to reach that 5 sigma level of statistical confidence. But even without definitive proof, the evidence is compelling. The detection of DMS on K2-18b suggests that life might be common in the universe. It suggests that there might be billions of planets with life. If that's true, then we're definitely not alone. We're part of a community of life-bearing worlds. We're part of a living universe. And that changes everything. It changes how we see ourselves. It changes our values. It changes our priorities. If we're not alone, then we have a responsibility to find other life. We have a responsibility to understand it. We have a responsibility to protect it. We also have a responsibility to protect our own world. Because if life is common in the universe, then Earth's life is precious. It's unique. It's irreplaceable. The detection of DMS on K2-18b is a reminder of this. It's a reminder that we're part of something larger than ourselves. It's a reminder that we're not alone. And that, perhaps, is the most important discovery of all. Right now, at this very moment, You are traveling through space at 67,000 miles per hour. You're hurtling through the cosmos at incomprehensible speeds. You're part of a cosmic journey that began 13.8 billion years ago. And now, we know that you're not alone on this journey. Somewhere out there, 120 light years away, there might be other life. There might be microorganisms in the warm oceans of K2-18b, producing DMS as a byproduct of their metabolism. These organisms, if they exist, would be completely unaware of us. They would have no idea that we exist. They would have no idea that we're looking for them. But we know they might be there, and that changes everything. The detection of DMS on K2-18b is not the end of the story. It's the beginning. It's the first step in a journey that will take us to the stars. In the coming decades, we'll search for life on other planets. We'll find more biosignatures. We'll discover more worlds with life. We'll begin to understand how common life is in the universe. And as we do, our perspective will change. We'll realize that we're not special. We're not unique. We're part of a living universe. But we'll also realize that we have a responsibility. We have a responsibility to protect our own world. We have a responsibility to preserve life on Earth. We have a responsibility to be good stewards of our planet. Because if life is common in the universe, then Earth's life is precious. It's unique. It's irreplaceable. The detection of DMS on K2-18b reminds us of this. It reminds us that we're part of something larger than ourselves. It reminds us that we're not alone. And that, perhaps, is the most important message of all. We set out to explore the cosmos, and we discovered that the cosmos is far stranger and more wonderful than we ever imagined. The possible life on K2-18b is out there right now. It's ancient light traveling across 120 light years to reach our telescopes. It existed when the universe was young, and it's waiting for us to understand it. What will we discover as we continue to search for life among the stars? What will it reveal about the nature of reality, the history of the cosmos, the fundamental laws of life itself? I can't wait to find out. And neither, I suspect, can you. Thank you for joining me on this journey into the deepest mystery in modern astrobiology. If you found this fascinating, please share it with others who love pondering the big questions. Subscribe to Void Light Talks for more explorations into the cosmic unknown. Until next time, keep looking into the void. You never know what might look back.